तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we continue our discussion on the reliability problem. We had seen 2 stages in the previous lecture, so we continue and we move to the third stage where you have n equal to 3 more stages to go. So here we make decision for item or component B, and we have to decide how many we can buy of this component B. So the state variable will be S, that is the amount of money that is available. So the decision will be x2 equal to 1, 2, 3 and 4. Now what are the values that the state variable can take? The minimum value that state variable S can take should be the minimum money required to buy at least one of B, one of C and one of D, which means the minimum money that we should have is 80 plus 75, 155 plus 60 is 215, that is the minimum amount of money, and the maximum that we would have is if we had bought only one of A and spent 100, so the maximum that we would be having here would be 300. So if we start with state variable equal to 215 and we decide to buy one of B, so we spend 80 rupees on B to get a reliability of 0.7, so we would get 0.7, and out of 215 we have spent 80, so we have remaining 135 which we carry to the previous stage. So when we have 135, then the maximum we could get is 0.56, so this will be 0.7 into 0.56, which will be 0.392. Now we cannot be evaluating x2 equal to 2, 3 or 4 because we won't have money to buy the other C and D. So the bare minimum being 2 and 5, there is only one alternative that is possible. So we do this. So very similar to the previous table, we have to now look at the value of the state variable from 215 to 300, which means we have to look at about 86 values starting from 215 to 300. We do not individually consider all the 86 values, we look at the range in which the maximum value will remain intact, and wherever there is a scope to bring in another alternative, or wherever there is a scope for one of the numbers to change, we evaluate that separately. So this will be from 215 to 219, we can have only one option, which is this option. So we say from 215 to 219 we have only one option. The moment we have 220, now we see that something else can happen. When we have 220, we can buy one of B and spend 80, and with the balance 140 we can go here and the best one becomes 0.64. So we get 0.8 into 0.64, and x2 equal to 2 would give us 0.7 into 0.64. We cannot consider x2 equal to 2 because we would have spent 100 on B, which means we would be carrying 120 and we do not have anything. So we need at least 135 here. So there is only one option that is possible here, and that would give us a reliability of 0.448, and the only option is the best option. So this would hold till from 220 to 224, this will hold. Now the moment we have 225, we find some other options possible. We buy one and spend 80, so we have the remaining 145, and so we could get 0.7 into 0.72, and even here if we want to buy 2 of B and spend 100, we would still be having only 125. So only when the state variable becomes 235, there is a possibility of the next option coming in. So 225 to 229 would give us only one option, which would mean 0.504. So similarly we look at 230 to 234, the only option is we spend 80 here, and for the balance we go back to 150. So for the 80 rupees spent we get 0.7. Now for 150 that is available in the previous table, we find that we could get a reliability of 0.76, and therefore this number becomes 0.532 and once again 1. The moment we have 235, we realize that two possibilities exist. We could buy one, spend 80 and carry the 135, so spend 1, 0.7, buy 1, spend 80, so we get 155, and for 155 we get 0.765. Now we could spend 100, buy 2 of B, get a reliability of 0.75, and with the balance 135 we go back to this table and get reliability of 0.56. So two possibilities exist now, and so between the two we have to choose that one which is higher. We get 0.5355 and go back to 1. So like this we have to complete this table. This is a fairly lengthy table. So this would be valid for the range 235 to 239, and we would have another range coming from 240 to 244, and for this range we would have 0.56525 and 1. For the range 245 to 249 we would have 0.5852, should be 1. 250 to 254, 0.5985 and 1. 255 to 259 we have the same 0.5985, 1, and so on. Now all these are shown in these two tables. We first go to the previous table. Now 215 to 219 we have only one alternative, 0.392, that is shown here in the beginning of this table, and that is shown here as well. Now when we have the last one that is shown here is 250 to 254, which is this. Now for 250 to 254 we have two possibilities, so we quickly explain both these possibilities. One is we decide to buy one of B, x2 equal to 1, which means you spend 80. So spend 80 with a reliability of 0.7, we see 0.7 here in the first part here, we see a 0.7 here, and with the remaining 170 we go back to the previous table and we could get 0.855. So we have 0.7 into 0.855, which is 0.5985. Now the other possibility of buying 2 of B, x2 equal to 2, which you can see there in the third column of the table, x2 equal to 2 in green, and there we realize that we buy 2, we spend 100, get a reliability of 0.75 which is shown here, and we spend 100, so for the balance 150 you could go back to this table and get a reliability of 0.76. So you have 0.75 into 0.76 which is 0.57 which is shown here. Now between the two 0.5985 is higher, so the best value is 0.5985 with the best decision at 1. The next table we continue this from 255 to the maximum 300, and we now have several alternatives coming in. We will just go through a couple of instances of calculation. For example, let us look at the case when the state variable is 270. Let us say we are here at 270. Now there are 3 possibilities. For example, when you could decide to buy x2 equal to 1 and get a reliability of 0.7, and so 270 we have spent 80, so there is a balance of 190. So 190 would give us another 0.855, so you would get for 270 0.7 into 0.855 which is 0.5985. Now we could also consider x1 equal to 2, spend 100, get a reliability of 0.75. Now out of 270 we have spent 100, so we have 170, and for 170 you go back to the previous table, you get 0.855. So this number is 0.75 got from here into 0.855 got from here, which is shown as 0.64125. Now we could also consider x2 equal to 3, so spend 120, get a reliability of 0.8, there is a balance 150 which is carried out, that 150 would give us 0.76, so we get 0.8 into 0.76 which is shown here, which is 0.608. We cannot consider x2 equal to 4 because x2 equal to 4 would mean you spend 140, so you have a balance of 130 that is carried to buying C and D, which is not enough, we need a minimum of 135. So we do not look at the fourth one. So there are 3 alternatives possible. Now among the 3 the best one is 0.64125 with the best decision at x1 equal to 2. The moment we come to 275 we realize that all 4 options are possible. So when we have 275 the fourth option is possible. So you could buy 4, spend 140, get 0.85, 0.85 is shown there, and spend 140 out of the 275 to carry 135, and for 135 you get 0.56. So you have 0.85 into 0.56, 0.476, but meanwhile the rest of the reliabilities would have changed, so the best value is again 64125 among the 4 values that we have computed. So like this we complete this table and go up to 300, and we also realize that for 300 the best one would be to buy 4 of this. So we have completed the third table, we have only shown a part of it here, the entire table is shown here as 2 tables in this slide. So the recursive equation here would be F3, I have 3 more stages to go, I have S state variable, S rupees available with me, I decide to buy x2 units of this, so I get a reliability of R of x2 into F2 star of S minus C of x2. I start with S, in order to buy x2 I spend C of x2, so S minus C of x2 I carry it to the previous table, F2 star of this. Now the best value F3 star is to minimize this, so F3 star would be to minimize F3 of S x2 subject to the condition that C of x2 is less than or equal to S. So I cannot exceed the amount that I have, plus more of course, so etc. So this is how the third table is completed. So at the end of the third table we had the state variable taking value 300 which is shown here, and the best value is 0.686375 with x equal to 4. Now we go to the last stage, which is the stage here. We have 4 more stages to go, so we go back and look at n equal to 4, We now move to n equal to 4, 4 more stages to go. So we are at the beginning here and we have 400 available with us. So S is the state variable, which is the amount of money available. X is the decision variable, or x1 in this case is the decision variable, where we like to choose the number of parallel units of A that we are going to have. So x1 can take any one of these 4 values. So you have x1 equal to 1, 2, 3 and 4, and we have 400 that is available with us. So we evaluate when x1 equal to 1, you have a reliability of 0.6 that comes out of it. You spend 100, so there is a balance of 300 that is available. So we go to the previous stage n equal to 3 and find out that for 300 the best value is 0.686375. So this multiplication would give us a value 0.411825. Now we can consider x1 equal to 2, and when we have x1 equal to 2, we get a reliability of 0.7. Then out of the 400 we spend 130, so we have a balance of 270, and for 270 from the previous table we would get 0.64125, and when we multiply these two, 0.7 into 0.64125, we would get 0.448875. Now when x1 equal to 3, we get a reliability of 0.8, and we spend 150 out of the 400 available. So we have a balance of 250. So we go to the previous table to find out for 250 the value is 0.5985. So this is 0.5985, and this multiplication 0.8 into 0.5985 gives 0.4788, and for x1 equal to 4 you could get a reliability of 0.9. We spend 170, so we have a balance of 130, 230, which would give us 0.532. We spend 170, there is a balance of 230, so you get 0.532. This on multiplication also gives us 0.4788. So now the best value, which is f1 star of S1, happens to be 0.4788, and x1 star we have two values which are 3 and 4. So we also have to write the recursive relationship. So for this the recursive relationship will become f1 star of S1, f1 of S1 x1 would give us R of x1, the reliability that you get, multiplied by f2 star or f4 star of S1 x1 would give us f3 star of S1 minus C of x1. That is, we have S1 equal to 400 here, and out of which we can take any one of the 4 values. There is an associated cost, so 400 minus that cost goes in to the next stage from which we took these values, these 4 values. So this is the recursive relationship. Now as far as the solution is concerned, we have two possibilities, x1 equal to 3 and x1 equal to 4. So we have some kind of an alternate optimum. So we look at both these cases. We look at the case x1 equal to 3 and x1 equal to 4. Now x1 equal to 3 would mean you spend 150 and there is a balance of 250. Now going back to the 250, you would get x2 equal to 1 for 250 here. So this gives us x2 equal to 1. So from 250 x2 equal to 1 means you have spent another 80, so you get 170, and now you go to 170 here, you get x3 equal to 4 from here, so 90, so there is an 80 that is remaining, so you would have x4 equal to 4. Alternately, when you have x1 equal to 4, you have spent 170, there is a 230 that is remaining, so from this you get again x2 equal to 1. So from the 230 you have spent 80, so 150 remains. So for 150 you would get x3 equal to 4, which means you spend 90, you have another 60, so that would give us x4 equal to 1. So there are two solutions that we have here, one is 3144 and the other is 4141. 3144 would mean 3144 and the other would mean 4141, both have the same 0.4788 reliability. We look at one more example where we consider decision variables taking discrete values. I get S of I, which is the salvage value. I have to buy a new one, so minus C or S of 0, they mean the same. Now I have a new machine with age 0, so I have plus P of 0. I have the profit associated with the new machine. I have a maintenance cost associated with the new machine. And then at the end of the year I go back, so I have to make a decision Fn minus 1 star, but the age of the equipment is 1 at the end of the year. So I have Fn minus 1 star of 1. So these are the recursive relationships with which we will work, and then we will make a table and proceed with our calculations. This is n equal to 1, one more stage to go. Decision is to keep or replace. The age is given by 0, 1, 2, 3 and so on. So we get into a situation where the age is 0 and I have one more stage to go, I keep the machine. So when I keep the machine, my decision would be here. So when I keep it, it is P of I minus M of I, 200 minus 10, which is 190. I do not have anything else to do, so I have 190 which comes in. Now when I have one more year to go and I have a brand new machine, I already have a brand new machine, so even if I decide to replace it, we assume that when you sell a brand new machine you get 800, you incur another 800 to buy, so they cancel out, and then you have a new machine, you have P of I and M of I, so you get 200 minus 10, which is again 190. Now when I have a machine that is 1 year old, I have P of I minus M of I, 180 minus 15, which is 165. When I decide to replace, I sell this, so I get 700. I have to buy a new one, I spend 800, so net is minus 100, and then I make 200 minus 10, 190, so 190 minus 100 is 90, so you have 90. So we can complete the rest of this table, and that is, we will show it again. We do not have this Fn minus 1 star coming in because we have only one more stage to go. So when the age is I, and when we decide to keep, the value will be P of I minus M of I, and when we decide to replace, it will be S of I minus C plus P of 0 minus M of 0. So that is shown as a first table here. For example, the 190, 190, 165 and 90 can be seen here. Now when I equal to 2, we get 140, which is this 160 minus 20, and to replace we would get a 40 which comes like this. 650 plus minus 800 is minus 150, and then you get a new machine plus 190. So 190 minus 150 is 40, and that 40 is shown. Like this we complete this table and go up to I equal to 8, to write 5 and minus 210. Now when we have n equal to 2 more stages to go, and I decide to keep. Now when the age of the machine is 0, even though I have 2 more stages to go, I decide to keep. So the expenditure would simply be, if the age is 0, then it will be P of 0 minus M of 0, which means whatever be the situation, if I decide to keep for that age, this is going to be 190. Now when I decide to keep a 0 1, at the end of the year the age will be 1. So I go back to the previous table, and when the age is 1, the best decision here is 165. So I get 190 plus 165, which is 355 here, and that 355 is shown there. Now when I decide to replace, as long as the age is 0, for that year the value is 190. Now at the end of the year the age is 1, so go back to the previous table, the best decision is again 165, so you get 355. Now when I have a 1-year-old machine and I decide to keep, the money will be 165 for that year, and then at the end of the year the age would become 2. So go back to the previous table and see what are the values for 2. Now that is shown here as 140 and 40 here. So now coming back, when I have n equal to 2, no matter what this n is, if I decide to keep and if the age is 1, the profit is 165, which is shown here, which comes here. Now the age being 1 and I decide to keep, at the end of the year the age will become 2. So go back to the previous table and see for age equal to 2, the best decision is to further keep and add a 140, so this will be 305. Now when n equal to 2 and I decide to replace, the moment I decide to replace, no matter what n is, if the age is 1, then I get 90 for that year. Now when I replace, at the end of the year the age of the equipment is 1, so go back to the previous table and see what is good here. So 90 plus 165 equal to 255, so that is shown here as 305 and 255 respectively. Similarly you can work it out, but you can work it out only up to I equal to 7 here, because you cannot work out I equal to 8 because you need I equal to 9 for this. See, wherever you keep, you realize that you are picking something from the previous table, but 1 to the right, because the age goes up by 1. Now since we have data only up to I equal to 8, we cannot do I equal to 8 here, because that would require numbers for I equal to 9 of the previous table. So you do only up to I equal to 7 and write this. Now similarly we can continue with this, and all these are shown in this table now. For example, when you are at n equal to 3 and you decide to keep, and I equal to 0 and decide to keep, that 190 comes because no matter what n is, if you decide to keep a 0-year-old equipment, you get 190, which is from the first table, which is this 190. Now when you decide to keep, at the end the age is 1, so go back to the previous table, the best is to choose between 305 and 255. To choose between 305 and 255, the best value is 305, so add 305 to 190 to get 495. Similarly when you decide to replace, for that year it is 190, the 190 comes from I equal to 0 replace this 190. moment the age is 0, no matter what n is, you get this 190. Now you have already replaced it. At the end of the year the age is 1, go back to the previous table and realize that 305 is better. So 190 plus 305, 495. You will also realize that this column will have the same number coming in for all of them. It makes more sense to start looking at it from the second column where the numbers will be different. Now when you are at n equal to 3, you can proceed only up to I equal to 6, you cannot go beyond because you do not have the, you cannot do I equal to 7 because you do not have I equal to 8 for n equal to 2. So like this we proceed and do it till n is equal to 8. Because we have data here for I equal to 8 up to 8 years, now we can go back and complete this table up to n equal to 8 and you have only one entry there. Now once this table is completed, we can start evaluating the decisions depending on where we are. For example, next, from this table you can compute the cost and the strategy when you are given number of years to go and age of the equipment. For example, if we are looking at n equal to 3, 3 more years to go and the age of the equipment is 1. Now let us go back and see what the decisions are. Now go back to the previous table. When I am at n equal to 3, I have I equal to 1. Now for n equal to 3, I equal to 1, when we keep, the value is 428, when we replace, the value is 395. Higher one being 428, we decide to keep for the first year. So we decide to keep. Now once you decide to keep, at the end of that year the age goes up by 1. So go to the previous table n equal to 2 and look at age also equal to 2. So n equal to 2, age equal to 2, to keep it is 263, to replace it is 205, so decision again is to keep. Now the decision is to keep at n equal to 2, I equal to 2, so age becomes 3 at the end of that year. So go back to n equal to 1 and I equal to 3, so decision would be once again to keep. So in this case, when n equal to 3 and I equal to 1, the decision would be to keep. Now go back, next table, next. Now when you have n equal to 7 and I equal to 2, now let us see what we do. Now go back to the table. At n equal to 7 and I equal to 2 is this next one. We have 763 and 768. So the better decision would be to replace for the first year, to replace. Now when you replace for n equal to 6, you have to look at I equal to 1 because you have brought a new machine. So for n equal to 6, look at I equal to 1, so decision would be to keep. Now when you decide to keep at I equal to 1, then the age goes up by 1 more, so you have to look between 558 and 563, so decision again is to replace. At n equal to 5, decision is to replace. Now go back to n equal to 4 and look at age equal to 1 because we have replaced it. So n equal to 4, age equal to 1 is between 523 and 518, 523 being higher, decision is to keep. Now age becomes 2, go back to n equal to 3 and I equal to 2, the relevant values are 358 and 345, so once again the decision is to keep. Now go back to n equal to 2, I equal to 3, so 218 and 155, once again the decision is to keep. And now with n equal to 1, between 95 and minus 60, decision again would be to keep. So these would be the decisions. Now for this equipment replacement problem, now once the table is drawn, now depending on the given values of n and I, we could go back and look at the table and try to find out what the corresponding decisions are. The only drawback in some sense is that when we begin the problem with say with 8 years data, then with every stage we are able to evaluate one less. So we can go only up to n equal to 8 in this problem, we cannot go beyond that, and we also realize that the alternatives that we have are also becoming lesser and lesser. Alternately, if we have more data here, the other thing that will happen is the table will become too cumbersome. So depending on the data that is given, depending on the values of Pi, Mi and Si, one can construct this table. Part of this table is shown in the board, while the complete table is shown in the PowerPoint slide, and then depending on the value of n and the value of I, depending on how many stages we have, how many years to go, and the age of the equipment, we go back into the table and then we would complete this. Now coming back to this, for n equal to 7 and I equal to 2, the decisions are shown. Whenever we decide to keep, then go back to the previous stage, go back to the previous table and shift at I plus 1, move 1 to the right, and so on. And when you replace, you should look at I equal to 1, because you have bought a new machine. At the end of the year, the age of the machine will be 1. Right. Next. Now from after this example, we now start looking at problems where we look at variables that have continuous values. So far we have seen 3 examples, and in all the 3 examples the decision variables had discrete integer values, and now we look at examples where the decision variable would take continuous values. So let us look at some simple problems that we are familiar with, problems we could even know the solution to these problems, but then we will try to show how we apply dynamic programming to solve these kind of nonlinear problems. Now the problem that we choose is to minimize x1 plus x2 plus x3 subject to x1, x2, x3 equal to 27, xj greater than or equal to 0. There is no integer restriction on the xj, xj's can take any continuous values. It is a nonlinear problem because of the constraint which exhibits nonlinearity. There is a product form in the constraint. Now let us first define the state, decision variable and the criterion of effectiveness for this problem before we proceed. Now here there are 3 variables and we will be solving them one at a time. So here in all these kind of problems, the stage is each variable. Each variable is a stage and we will be solving for one variable at a time. The state always represents the resource that is available. There is a single constraint. We do not know what this constraint physically represents. In all the 3 earlier examples, we knew there is some physical entity associated with the problem, like age of the machine or the money that is available or the city in which from which the person moves. Here we do not know what this constraint is, so we simply say that the state variable is a resource available. Decision variable are the values of x1, x2, x3, and the criterion of effectiveness is to minimize z. So we now start the problem with n equal to 1, one more stage to go. Now when we have one more stage to go, we are solving for the first variable. So basically we are at this part of the problem. So we try to minimize an x3 subject to x3 equal to something, xt greater than or equal to 0. So f1, one more stage to go. I have s1 let us say, and I am trying to solve for x3. Now this will be equal to x3 because this is the function that we are trying to minimize. Now the f1 star of s1 is the minimum value of x3 subject to x3 equal to s1, x3 greater than or equal to 0. Now what we are trying to solve here is minimize x3 subject to x3 equal to s1. S1 is available for allocation to x3, which means something has been allocated to the product x1, x2 and available for x3. and because it is an equation we have to allocate everything that is available to this variable x3. If this were an inequality, then we have a choice of whether we allocate everything to x3 or something less and so on. Now because we have an equation here, now all of S1 has to go to x3 and x3 has to be greater than or equal to 0. Now we are going to make one assumption that since x1 xj is greater than or equal to 0, we assume that the state variables cannot be negative. So state variables themselves are greater than or equal to 0. So straight away for this case you have x3 star equal to S1 because you have to allocate everything, and F1 star of S1 will be S1 because we allocate everything. So the minimum value that it will take is S1, it can't take anything lower than that. Now when we have two more stages to go, n equal to 2, two more stages to go, F2 of S2 x2. Now here we are somewhere here in the middle trying to solve for this. So I have S2 resources available which I have to allocate to x2 in a certain form. Now this will be x2 plus, because the objective function is x2, plus if I have S2 and I allocate x2 here, then S2 by x2 is carried as S1 because of the product form of this. So whatever is carried as S1 is actually S2 by x2. So this will become F1 star of S2 by x2. Once again we assume when we have two more stages to go that there is some S2 available here which is obtained after something is allocated to x1. Please remember it's not subtraction, it's a product form. So something is allocated to x1 and there is an S2 that is available for allocation to x2 and x3. So we allocate something to x2, so S2 by x2 will go to x3, or we are looking at a constraint which is like x2 x3 equal to S2. So if this x2 goes, then whatever is balance will be S2 by x2 will go as x3. So you have F1 star of S2 by x2. Now F2 star, the best value would be that value of x2 which minimizes, so minimum of x2 plus. We know that F1 star of S1 is S1 itself. So F1 star of S2 by x2 will be S2 by x2, subject to the condition of course x2 greater than or equal to 0, less than or equal to, need not be because it is a product form, so it need not be less than or equal to S2 because of a product form. If it were an addition, then you could go back and say x2 should be less than or equal to S2, here it need not be. Now this we need to minimize, and the minimum is obtained by equating the first derivative to 0. 2 equal to 0 gives 1 minus S2 by x2 square equal to 0, from which x2 equal to plus root of S2, plus root of S2 because x2 is greater than or equal to 0. So x2 star is equal to root of S2 and F2 star of S2 is x2 which is root of x2 plus S2 by root of S2 which is 2 root S2. Now we have n equal to 3, 3 more stages to go. Which means we are making a decision for variable x1. So we are trying to solve x1 plus x2 plus x3 subject to x1 into S2 equal to 27. So something out of the 27 goes to x1, and because of the product form whatever is carried to x2 x3 is 27 by x1. So we have F3, we start with 27 and we decide to allocate x1. This will be x1 plus F2 star of 27 by x1. That is because from this 27 we have given an x1 here. So whatever gets carried as S2 is 27 by x1. So now F3 star of 27, so the best decision will be that value of x1 which minimizes x1 plus F2 star of S2 is 2 times root of S2. So F2 star of 27 by x1 is 2 times root of 27 by x1. Now this, the minimum value of x1 is got by differentiating with respect to x1 and setting the first derivative to 0. So df3 by dx1 equal to 0 gives 1 plus 2 root 27. Now this is x1 to the power minus half, so minus 1 by 2 x1 to the power minus 3 by 2 equal to 0. Now this 2 and this 2 gets cancelled, so we have root of 27 into x1 to the power minus 3 by 2 is equal to 1. Now this is 27 to the power half, so 27 to the power half into x1 to the power minus 3 by 2 equal to 1. So x1 to the power minus 3 by 2 is equal to 27 to the power minus 1 by 2, from which we would have x1 equal to cube root of 27, 27 to the power 1 by 3, which is 3. So the best value of x1, which is x1 star, is given by x1 star equal to 3. Now f3 star of 27 will be 3 plus root of 27 by 3, which is 3 plus, so 2 root 27 by 3, 3 plus 2 times root of 27 by 3, so 3 plus 2 into 3, this is 9. Now x1 star equal to 3, which means we have given 3 to the variable x1, so the product whatever goes as S2 is 9, so S2 is 9. Now x2 star is equal to root of S2, which is root of 9, which is 3 plus 3, and because of this we have S1 will be S2 by x2, S2 by x2, so we have 9 by 3, which is 3, and x3 star is equal to S1, which is also equal to 3. So we have x1 equal to 3, x2 equal to 3, x3 equal to 3. Minimum value will be 3 plus 3 plus 3, which is 9. So we have actually solved this problem to get the solution, even though the problem is the solution is well known even by looking at the problem. Now there are a couple of other things that we need to address. One is this: when we made this differentiation and said we set the first derivative to 0, we got the value of x1 equal to 3. We have to make sure that x1 equal to 3 actually minimizes. So that is verified by looking at the second derivative, and from this one would realize that the second derivative would be positive because there is a minus term here, and differentiating further would give us another minus 3 by 2 x1 to the power minus 5 by 2, which would make the term positive for x1 positive. When x1 positive, x1 to the power negative term would is also a positive number. So second derivative is positive, indicating that it is a minimum. Here again the first derivative equal to 0 would give us this 1 minus s2 by x2 square equal to 0. If we do a second derivative, we would again have a plus term coming in, and x2 to the power something, x2 to the power something is again a positive term. So here again this value plus x2 minimizes this. We have to ensure that not only do we set the first derivative to 0 and get the minimum or the value, minimum or the maximum, we also have to look at the sufficient condition and look at the second derivative to 0 and check that it actually minimizes. In both these cases, setting second derivative equal to 0 gives a positive coefficient, which means these corresponding values minimize the objective function. The next thing is, in these situations, these are problems where the decision variable take continuous values, they do not take integer values like the 3 previous examples, they take continuous values. For example, it is incidental that the values were nice round integers, but on the other hand, if this were not 27 but this were something else, then we would get continuous values here. We would get, if this were say 30, then each would be cube root of 30 to get 3 times cube root of 30. So the decision variable could take continuous values here. Now in all these problems we need not separately write the recursive relationships, unlike in the discrete case, where whenever we use the tabular form to solve, it is necessary for us to write the recursive relationship separately. In all these cases, when we work with continuous variables, the equations themselves represent the recursive. After all, recursive relationships are written and from which they are solved. So one need not explicitly write the recursive relationship, nor is it necessary for one to write a general recursive form. We have done it for each and every stage as it is. The other thing that we need to look at here is there is a single constraint. Most of the problems that we will be addressing would be single constraint problems, and in this case it is an equation. Now because the single constraint is an equation, and when we have one more stage to go and we have one variable to allocate, we would always get into a situation of x3 equal to s1. So whenever we have an equation in the first stage at n equal to 1, we do not optimize. Whatever resource that is available for this variable, if the constraint is an equation and when we have one more stage to go, we do not optimize, we simply allocate as we did here. Because x3 equal to s1, whether you minimize or maximize or whatever be the thing, x3 is forced to take the value s1. So there is no optimization in this case. Whereas in the subsequent stages n equal to 2 and n equal to 3, there is scope for optimization. So here we evaluate the function and then we realize we have to minimize something. So you set the first derivative to 0 and then you optimize here and then show that actually at root of s2 it minimizes by looking at the second derivative and showing that the second derivative is positive. So in all problems involving equations, we do not optimize in the first stage or stage n equal to 1, we optimize only at subsequent stages. So whenever we have an inequality coming in as a constraint, then there is scope to optimize right in the first stage. We need to look at those aspects as well in the subsequent examples that we will be looking at. We would also be trying to address problems which have maximization instead of minimization. Of course the methodology would more or less remain the same, it will not change, except that when we address maximization problems and when we optimize, we have to go back and say that the second derivative is negative at the value. So in that case we need to again look at the second derivative, set it to 0 or set it evaluate the second derivative at the optimum point and show that the second derivative is negative, indicating maximum. So we will be looking at some more examples which involve maximization, which would involve inequalities and which would also involve linear functions in due course in the next lecture.